mouse.
So, I took a few classes with Dan a few years ago, and last year I decided as an exercise to work out an LALR1 parser just to get more familiar with the theory behind it. And I found, of course, there are two ways to generate LALR1 parser tables. One is you do LR1 parser tables and perform a quotient operation. The other one is use this relational expression and a transitive closure to get a fast, direct computation, right? Well, the problem is there's a lot of bookkeeping in the relational expression version, right? In order to avoid infinite cycles, and I was no good at that. Apparently, my software engineering didn't work, and so I abandoned it for a while until I realized I could just do what Dan taught me to do and generate the bookkeeping code, right? So let's just do a brief review. This isn't that necessary, but we'll remember the terminals T, non-terminals N, vocabulary V, right? For words in the general vocabulary, including the non-terminals, we use alpha, beta, delta. Capital A, B, C are non-terminals. X, Y, and Z are words in the terminal language. And lowercase Roman are just terminal letters. And of course, the double arrow star give you the derivation. And K, alpha colon K is the longest prefix of alpha, which is a word in V star, of length K or less. And finally, an item has this form as a production with a dot telling you where you are in the production, right, when you're looking at some word. And I'll look at X. So, hope that wasn't too brief. We don't really need that very much. The relational expressions we're going to be looking at are just these. It's just regular expressions on, except for the inverse, on relational variables, right? In other words, we can have a primitive relation, a union of two relations, a composition of two relations, the transitive closure of a relation, or the inverse of a relation. These are for finite relations, that's why you can do the inverse. If you wanted to do infinite, you just drop that inverse, you'll be fine. Sets are interpreted as filtering relations if you define on an appropriate domain for the rest of the relation expression. You just have, for each element in the set, A twiddles A, and the rest of the elements in the domain don't twiddle anything, right? So, now these are some example. This is an example of how you use these things. So these are fairly simple. X begins A if you have a rule where X is in the production and the prefix before that reduces to null, right? Or can reduce to null. Say X can end A in essentially a symmetric way if the suffix reduces to null. X adjoins Y if the grammar has a rule that A goes to alpha, produces alpha X, gamma Y, beta, and gamma reduces to null. X terminal Y if Y is terminal and X is equal to Y. In other words, that's one of those filtering relations. It's just the set T, right? Let's go down here. First of, a first of x if x reduces to a word such that a begins that word. Right. A follows y if s, the start symbol, reduces to a word in the vocabulary star, not necessarily a terminal word. Alpha, y, beta, and a first of beta for some alpha, beta, and b star. Right. In other words, we have some production where y appears in the word and then it's followed by a eventually in some terminal instantiation. So we can define first of to be terminal begins star, right? And follows to be terminal begins star adjoins inverse ends inverse star. In other words, we have a terminal. It begins some chain of non-terminals, which adjoins another terminal. Right? This adjoined inverse means the one preceding. Right? It goes where it's up there. We're talking about going from y to x, except actually y, and then we find something that ends, some terminal that ends x. Or actually, I'm sorry, any non-terminal ending x will do. Right. Let's see. The nice thing is we can find adjoins as it stands right there is a quadratic computation. If you directly implement that, you can get a linear relational expression where use these definitions, right? A production points to, or an item, I'm sorry, a position A, this position points to x, this one passes any x, and this one we pass null x if x reduces to null, right? So adjoins is you inverse points, right? So you take a non-terminal and you find an item that points to it. Then you pass any once, and then you pass any number of null, things that reduce to null, and then you see what you point to, right? So, and that's linear in the size of the grammar. So that's a very nice way to express things, right? We can do this directly. We're going to project into a space of graphs, right? If you noticed, these are all these relations have different types in and out, right? Now we're going to go into a homogeneous graph space of vertices, okay? Vis-a-vis. We start out with a domain and codomain of a relation. Right? We have an input correspondence, takes the domain to it's misprint. To be V, right, which is 1 to 1. An output, which takes the codomain to the vertices. The input and the output nodes do not overlap, even if the codomain and domain are the same, right? We take them to unique nodes. And the RE of VE, that is the RE is the edge relation. So if you apply the edges to some set of inputs, or I'm sorry, to the destinations of all edges do not intersect with the input nodes, right? So no input has an edge entering it, and no output node has an edge leaving it. And finally, RE is such that if you compute the transitive closure of the edges, you get the input nodes of X relate to the output nodes that they twiddle in the transitive closure of the graph. Okay? And it's a fairly simple construction, right? Like I said, we need a homogeneous space of nodes. do this the simplest possible way, and we'll get smarter as we go along, right? That's the way I learned it from Dan anyway, or my interpretation. So the primitive relation is simple, as I said. These two could be the same domain. We just project them into the graph space, the vertex space, and reflect the relation P by edges on the graph. Right? A union relation, we simply construct. Right, this is just the non-deterministic finite automata construction, right? Except it's quantified over every element in the domain, right? And likewise for composition, right? We just chain those together. You notice that the output of one has to be equal to the output domain of the one has to be the input domain of the other. Now the star relation is really the trick, right? In that we take each input element, given an input node, we have to have the same domain and codomain, right? They have to agree. We can map it to directly to the output node, or we map it into this loop in node, which then goes to some corresponding loop out node. The loop out node goes directly to the output, or it goes back to the loop in node, right? So we're just computing a direct loop. And yeah, inverse you can do on your own. Now, to compute this relation, we'll do Tarzan's algorithm, which I have a distinctly non-schemy version written down here, which I adapted from Sipu and Soisalon, Soinen, and parsing theory. And this, of course, came from a 1972 paper by Tarzan. So given a graph constructed like this, or any graph, and a function that's defined, you have a function that's defined on the nodes, and you want it to define inductively a function, so you have G naught defined on each node. You want to define G to be the union, or the join, or whatever, you know, or the join on all of its successor nodes, right, and itself. Then you can just go through what this function does. It puts everything on a stack. As you go through the graph, you have an ordering based on a depth first traversal, right? And when and you get that by just pushing A on the stack, and then as you go through, if you encounter a C that isn't marked, right, then you explore that node. And when you come back, you compare you're computing this minimal node of the strongly connected component that it belongs to. And so you compare your candidate with the candidate that comes back for C, and you take the minimum of those two. And if it is marked and it is on the stack, then you just take the stack minimum of your candidate in C. And then after those two steps, you just take the union of G of A with G of U. Right? That's an update. The real trick here is that you never pop anything off the stack until you finish exploring the strongly connected component it's a part of. Then you pop everything off the stack, right? And that becomes the SEC of A and the SEC of B, right? And you can just equate G of B for every B in the SEC with G of A. So it's kind of a nice algorithm in that there's propagation in two directions, right? One is you're finding out forward who you're connected to. As you come back, you're transmitting the information of what your outputs were, right? It has to flow backwards. Now, the problem with this compilation method is that you have to construct the relations as graphs. right? Which is really a slow method to do things, because your domains and codomains have to be completely instantiated. And when you're doing grammar analysis, you're using item sets as your domain of your machine, right? And so if you instantiate a power set of a power set, you're doomed, right? But on the other hand, we don't have to have any typing, right? So how to overcome this problem? We're going to do an object orientation of the nodes. We're going to teach each node, when we create it, how to find its own successors. We're going to build that knowledge into it. On the downside, each node then has to know what has come before, so that when it allocates a successor node, it gives it the right knowledge, right? When it hits a cycle. Or for that matter, what its output is, right? Because you have to keep, like I said, you have to keep, the information flows both forward and backwards. So this is the adaptation of the star relation graph. Right here are our previous nodes. Now these are basically lists with a letrec, you know. So they have a list of recursive functions, and they know each node has a pointer to this database, or a dictionary, sorry, and this one has a pointer to this dictionary. And these take the domain elements, not the nodes, to information. Have I been marked? Am I on the stack? Where am I on the stack? What are my outputs? What's my strongly connected component, right? So now we've taught it that information. You do the same for all those graphs, right? We have to have some sense of a type system for doing this. I managed to get away with a very crude type system. But you need, for any of your types, to be able to construct a dictionary on that type to any other type. Now, it may be, I'm sorry. It may be that you can get rid of a lot of that everywhere except for the loop in and loop out, right? The recursive calls. You don't really need all that information, but it's not as easy as just wiping out the database, because, like I said, you have to keep track of the information flowing backwards. Now, the final step, nothing here depends on being runtime. You lift the functions that you were calling up above the runtime creation. You just turn everything into macros, and you have yourself a compiler, right? Suddenly, that's where your Bison is in 100 lines now, right? So, well, as Dan would count them. I'm sure you all know how that works. Let's see. Now, of course, any good schemer has to wonder, where is the lambda and letrec, right? Because that what I've done there, that started out in 74, 77 by Hunt, and then there's been like 4 papers since then, one as recent as 2003 on this. But really, it's sort of not gone anywhere, which is too bad, because it's actually a very efficient formulation of this construction. We have tail recursion. How do we get mutually recursive relations? Now, one of the problems is people who look at this stuff are basically people who do logic languages, and they have their own problems. When you're dealing with instantiating instance variables, you have a whole slew of problems besides what we've done, right? We have a fixed ordering of evaluation. If you're doing general logic language, you have to decide all that stuff, and that's much harder. Now, but if you have a linear binary chain query, a set of linear binary chain queries, in other words, a set of relations like R1 of x, y, R2 of y, z, etc., where no relation appears more than once, that's why it's linear, then you can use this construction to bootstrap somewhat into that, and but you have to revert to an accumulation method. At least that's the way it's been formulated so far. because they were working on graphs, right? But the way we've looked at it, you can now see that in fact the graphs that we constructed were just finite representations of infinite graphs, right? And because they had that finite representation, it's basically a co-induction setting. You had a finite support of your relation, right? And likewise, a letrec, which corresponds to a context-free grammar in this context, right? That has a finite support as well because you have a finite domain and codomain. Every relation has finite support. And the way we can implement this is where we have where we have these nodes here, you can see that this is just the continuation, right? We're just giving the inner relation a continuation that goes back to here. Okay? For a general CFG, we can just tell it each continuation that it has to tell its outputs, right? For later follow-up. Now, that's one way to approach the problem. And, you know, this is fairly nice because you look at a live variable analysis now in a construction like this. I have to say, I haven't implemented any of this. This is all. I just want to do this because it nicely ties into Dan's work, I think, or at least what I've learned from him. You know, if you have your expression already in a graph, right? So your go-tos are gone. They're just the following nodes. A variable reference has live variables of the variable reference and the following code fed to the live variables, right? Which is recursive. Assignment, you know, you take the expression that you're assigning, its live variables, and here's why this is nonlinear. This has puzzled me for a while. You feed the following code into the live variables, and then you say not the variable that was assigned, right? You do a filter on what you got out. And then if, you just compose the live variables of each piece, and application, you take the union, and then the relation is the union of those four relations. Right? So I think that's a fairly nice formulation, a nice short way of writing a live variable analysis. Right? Now, what about Lambda? Really, the only question is how much we expect to mix with regular scheme, because that can be a problem. Otherwise, it seems fairly straightforward. Now, do we need letrec? This puzzled me for a while because it seemed like, didn't I learn in Dan's class that everything is can be made tail recursive? Why do I need letrec, right? But once we get higher order relations, then we can do CPS on the relations, right, and use the star operator exclusively if we like. And of course, we have the call CC relation. That's useful if you want to write a garbage collector in this language. Now, for a real language, we have to add a type system that can type scheme, which is hard, or at least the part that I use, or whoever the users use. You have to automatically generate dictionary constructors when they aren't specified, which is doable. And you'd like to be able to specify all the way down to bits and bytes if you want to write a compiler with this kind of thing. Right, and obviously abstract interpreters, garbage collectors, and wherever transitive closure is needed by a lazy programmer like me. So, all right, and those are the references. Okay? So I'm done.
Questions? Hearing none, we can proceed to the next.